Hi all, it's Dr. Patrick again. So all of the inferential statistics that we've discussed, previously share a set of assumptions, regression, ANOVA, correlation, and t-test all assume that the data involved are scores on some measure, whether it's IQ, height, income, scores on a measure of depression. They're all calculated from samples drawn from populations that are normally distributed. So normal distributions, remember I'm normal? And so, and everything is all hunky-dory in the world of research. But however, populations are sometimes skewed rather than normal. Sometimes researchers want to know about things besides those that can be measured. Research is often very messy and unpredictable and not so hunky-dory. So the violation of these assumptions, represents some sort of, good news, bad news situation. The bad news is that if the assumptions are violated to an alarming degree, the results of these stats can be difficult to, interpret, and they can also be meaningless. The good news is that to an alarming degree, it is an imprecise phrase and open to interpretation. So in many situations, violating assumptions of normally distributed data often do not make the results invalid or even alter them that much. Another piece of good news is that even when the assumptions of these stats are horrifically violated, there's a whole batch of statistics that researchers can use that do not have the same assumptions of normality and random selection, and it's called non-parametric statistics. So these non-parametric stats can be extremely useful, and descriptions of their uses and characteristics can be found in most standard, length stat books, and you can find them online as well. So one of the most commonly used non-parametric tests is called the chi-square test of independence. And this test is appropriate for use when you have data from two categorical or nominally scaled variables. It's called chi-square, not chi-square, just FYI. Long story about that, I learned the hard way in my first stat class in college. But with categorical variables, the cases in your sample are actually divided among the different categories of your categorical variables. For example, let's think about gender. This is a categorical variable, and the cases in the sample of human beings, guess what? They can be divided into what? Male and female, the two categories of the gender variable. When you have two of these categorical variables, you may want to know whether the division of cases in one variable is independent of the other categorical variable. For example, let's suppose you have a sample of boys and girls from the 5th, 8th, and 12th grades of school. So you may want to know whether your representation of boys and girls depends on their grade level, or if the division of boys and girls is about what you would expect independent of grade level. This is the type of questions that the chi-square test of independence was actually designed to answer. A more precise way of actually stating the purpose of the chi-square test of independence is this. It allows you to determine whether cases in a sample actually fall into categories and proportions equal to what one would expect by chance. Another example, let's suppose you work in a liberal arts college and you want to know whether the men and women in your college differ in their selection of majors. So what would I do? I would randomly select 100 men and 100 women and ask them to tell me their major. You would get the data presented, you would put it in a table. And what you would ask is, does this distribution of data represent a statistically significant gender difference in majors? But before you can answer that question, you need to know more information. Specifically, you have to determine how many men and how many women you expect to major in these three areas, just based on the number of each gender in each major in the sample. Let's just say I was going to say psychology major, English major, and biology major. So this is the type of question that chi-square test of independence will allow you to actually answer. So we're going to look at the chi-square test for goodness of fit, where we're comparing multiple 3 or more proportions, and then the chi-square test for independence. So goodness of fit. So this is used to check whether our previous or our old beliefs and probabilities is still true. We're looking, are there any changes over time? For example, maybe we have a belief that we work in sales and that there's no difference in sales by each month. So our null is, the probability of 1 equals probably, so on and so forth. And then our alternative is that more than one proportion does not equal to 1 out of 12. Since there's 12 months in a year. Our belief, though, is that our fourth quarter sales is going to equal 40% of sales, and it's same for all of the other quarters. And so you can see, once again, the null and then our alternative, that there could be any possible differences. All right. So our null is that, guess what? There's not going to be any changes. And then our alternative, we're just seeing that, there's going to be possible differences there. All right, so let's look at this. Let's look at this example of a grocery store. An owner of a grocery store chain suspects that there has been a change in the shopping pattern of his customers. He has always believed that his stores are equally busy regardless of the days of the week. So he wants to know whether some days are in fact busier than others. So what he does, he randomly samples 105 customers from the database and asks them which day of the week they go grocery shopping. And here are the results of the survey. And as you can see, our alpha is 0.05, so a 95% level of significance there. So let's keep going. So step 1, what do? We have to state the null and alternative hypothesis, right? Our null is there's no changes. Alternative is that there's going to be some differences there. Our next step is to state the rejection rules, right? So we reject the null hypothesis if our test statistic is greater than the critical value. Our step 3 is that we are going to find the test statistics, and this formula should look familiar. Where we're looking at the number of actual or new observations in a category and the expected number of observations if the null is true. So the I, just note, stands for each category. In the grocery store example, it's going to be the day of the week. All right. So now we have to find our step 3, find our test statistic, which is 5.6, using our handy dandy great formula there. Step 4, we're going to find the critical value. You should be very familiar with the degrees of freedom as well. We use that as well. And then step 5, we make our decision. And we fail to reject at the 0.05 significant level. And you can also use Excel in your spreadsheet to kind of plug and play. And there's also an Excel function as well. So now let's look at a chi-square test for independence. Okay, so this is one of my favorite examples because I do like to drink wine, and I'm a big Serena Williams fan. So let's just say we have a study in which we want to know the relationship of drinking wine and watching tennis on the TV. So we take a survey, right? We look at the number of people who drink wine and watch tennis, that's 16 people. The number of people who drink wine and don't watch tennis, 24. The number of people who don't drink wine and watch tennis is 4. And the number of people who don't drink wine and don't watch tennis is 56. All right, so our total sample is, 100. So from the survey, we look at our actual numbers, our observed counts, and we would do it just like this. So if you were setting this up in Excel or a mini tab, and I think in your handy dandy Excel spreadsheet, you'd be able to plug and play as well. All right, so we want to know the probabilities, right? So the probability of, individuals who drink wine, our sample size was 100, right? And we found out that the total that drink wine, how do we figure out the probabilities? It's 40 divided by 100, so that's 0.4. And so we get the probabilities for each one of these categories. So the probability of someone who doesn't drink wine, that was 60. 60 divided by 100, the people that watch tennis. So we go through each one of those. All right. And so recall that if two events, A and B, are independent, the probability of A times the probability of B. So if wine and tennis are independent, right, the probability of a person drinking wine and watching tennis, I mean, we can figure that out, right? So 0.4 times 0.2, 0.08, and our expected count is 8. So, and we would go through each one of those in order to figure out our expected count. All right. Also, if the two events are independent, we have our expected numbers as well. All right. And also our observed numbers for our expected numbers, as you can see here in my handy dandy chart. Drink, no drink, watch, no watch. So now we're going to go back through our steps. The first step, once again, we're going to state our null and alternative hypotheses. The null is watching tennis and drinking wine are independent. Alternative is watching tennis and drinking wine are dependent. What's our rejection rule? Once again, that's always step 2. You're going to reject the null if your test statistic is greater than the critical value. All right, and then what do we have to do? We have to find that test statistic. Here's your handy dandy formula. You can also do it in Excel as well. I believe there's a plug and play for you available, and you can also find it in Minitab. So our x squared is, our test statistic is 16.67. And then the next step, find the critical value, which is equal to 3.841, and then our step 5 is what's our decision? Well, we reject at the 0.05 significance level.